Okay, so we can start today's session. So mainly we will discuss about the some problems on compact spaces. Okay, so you see, in your first class, I had asked this question, and that if you consider the space R, and if you take the collection tau, we consist of R and empty set, and set of all means all subsets such that their complement is compact. So you have to check whether this space is a topology, means whether this collection is a topology, and then you have been asked whether it is strictly finite than cofinite topology. And the third problem was find all compact sets. Okay, so I think you have you did something about to show the why tau is a topology or not. So could you please quickly tell me? See,
Yes,
empty
sir,
set,
topology.
wait, empty set and R are in tau. So this is done. What about the second condition? Yes,
That intersection.
We can use Heine-Borel theorem.
we can use Heine-Borel theorem. What does Heine-Borel theorem tells you? I cannot hear you. I don't know why. I should increase the sound a little bit. It's 100%. Anyway, so is there anything? Yeah. So hello, am I audible now?
Yes, sir.
Yeah. Okay. So yes, tell me. So first, tell me about the union. So suppose U alpha such that this be an arbitrary collection of open set collection or arbitrary subcollection of this tau, right? So you have to prove that this union of U alpha belongs to lambda is open. So means this is not open, not yet. So you have to say this belongs to tau. So to prove that this union is in tau, so what you have to do? In which
R
set you
minus
look?
R minus this is compact.
Yes, you have to prove R minus union of alpha belongs to lambda U alpha is compact, right? Now
It's equal to intersection arbitrary intersection of AI complement means U alpha complement.
U alpha complement, fine.
And given that U alpha complement is compact.
Yes, is U alpha complement is compact, then
And we know that arbitrary intersection of compact set is compact.
yes, fine. Then
And
this is
then
compact, right?
yes.
Is it clear to everyone? Yes. Yes, no?
Yes, sir.
Yes, sir.
Okay, fine. So therefore this is compact, and so you can say the union is compact, right? So union is in tau, right? So what about the second condition? Take this kind of elements ui 1 less than equal to or less than equal to m be a finite collection. You consider intersection of ui, right? And take r minus this intersection 1 to n ui means union of 1 to n ui complement, right? Then finite union of compact set.
Is compact.
Yes, finite union of compact set is compact, right? This is compact, and so this intersection is in tau. So we are done with the first problem. So this is, so therefore tau is the topology. What about the second? Why the cofinite topology is strictly finite than this one? Look
Sir,
at the basic. Yes.
suppose any open sets in cofinite topology.
Yes. Any open set.
Yes, sir.
Then
we know that R minus U is finite.
R minus U is finite.
And we know that finite subsets are closed.
So
compact.
R minus union is
Compact.
Is it clear to everyone?
Yes, sir.
R minus U is compact, and
Hence
therefore
U belong to co-compact topology.
U belongs to this tau, right? Co-compact topology. Therefore, the containment happen. Now, why it is strictly finite? Can you give a counter example? Means,
Sir,
can you give an open set here which is not there?
Sir, we choose R minus close interval AB.
Yes, exactly. R minus close interval AB is equal to U. Then it is open in tau. So this belongs to tau, but it is not in co-finite topology, right? So now this question is a vertical. Actually, this is a very crucial problem, and sir given this problem to you to verify that there are some, I think, some sequential criterion and all those. And he thought that in this problem, if we take any set, then that set will be compact. Means actually, you know what you know, in a Hausdorff topological space, every compact set is closed, right? Fine. If your space is Hausdorff, then every compact set is closed. Clear?
Yes, sir.
Yes.
Yes, sir.
So, but actually, you can see that this space is not Hausdorff. Okay, you can see this actually this space is not Hausdorff, and therefore, so this is, so we can see actually sir was trying to give you some example where the compact sets are not closed actually. Okay, but I think this situation will not appear for this problem. I have tried to figure out all the compact sets, but able to find up to the closer sets. Means up to I found out that the all closed sets are compact, but could not find out more. I also asked sir about this problem, but he also told initially that every subset will be compact, but and later I had some example where their set is not going to be compact. So uh, in this problem also it can happen that all the closed sets are the only compact set, but we do not know. So if you have some counter example that there is some set which is not closed but still it's compact, then you can bring this problem. You can tell this. So if it is not, then I will do something, some uh, progress on this problem, but I could not give all the compact set at the moment. Okay. So can anybody have any idea? What about the compact?
सर कोफाइनाइट टोपोलॉजी में तो हमें एग्जांपल मिल गया था, बट सर इस बार जो को कॉम्पैक्ट टोपोलॉजी इसमें सर हमें नहीं मिला कि वो क्लोज मतलब ना हो और कॉम्पैक्ट हो.
हाँ हाँ, इसमें तो नहीं मिल रहा है ना.
सर मतलब को फाइनाइट में मतलब सारे सबसेट तो होते हैं कॉम्पैक्ट होते हैं और फाइनाइट ही सिर्फ क्लोज होते हैं. वहां से हमें मिल गया था कोई इनफाइनाइट सबसेट उठा लेंगे तो कॉम्पैक्ट तो होगा ही बट क्लोज नहीं होगा.
हाँ. अब इसका क्या करें? ये बताओ कि ये जो R है, tell me one thing, do everyone know Hindi? Means if anyone present here who do not know Hindi? Yes. Yeah. Okay. So first try to see whether R is compact here. Is R compact set of R? So is it a compact space? Is it a compact? Let us verify. So take R subset of union of I belongs to some lambda ui. Fine. This lambda is an arbitrary index set. This is not countable. Okay, not uncountable. So we do not know. It's arbitrary. Okay. So now R subset of ui, where ui are open in where R comma
R
tau,
tau.
right? Yes. So now you choose any one. So suppose u1 belongs to this set, such that I belongs to lambda. We are taking any set. Then what happens? What do we know? R minus u1 is,
Compact.
yes, it is compact. You also know something more. What? What do we know?
Closed
R
in line.
minus u1 is subset of
Finite union.
finitely many element. Who is finitely many element? Tell me the elements. Yes, you are right that it will be a finitely many element, but which one? First, give me this one. So you see here, union I belongs to lambda minus this one ui, right? Fine.
Yes, sir.
Clear it is? Is it clear? I think so. Now this space is a compact space. This is compact, right? So from the definition, this has a finite subcollection, means there exist say I1, I2 up to some In belongs to where? This lambda minus 1 singleton set, such that this R minus U1 is contained in 1 to n say j u I j, right? Because this is compact. Now you take R. So they are now therefore R contained in this union j equal to 1 to n u I j union u1. Fine. So we have a finite subcollection. Fine. Therefore R is compact. Fine. Now now take say T, or let me take not T. Take suppose C subset of R, and C is closed with respect to or closed in R comma tau. Fine. Then what can we say about this result? Closed subset of a compact set is
Compact.
what?
Compact.
Yes. So therefore C is compact in R comma tau. One more thing here. From this definition, I have taken a closed set. You can initially say why we are using this argument that the closed subset of a compact set is compact. You already know that C is a compact if C is closed in here. But by definition, C is compact in R with usual topology. Okay. This is by definition. Means if we have a C is a closed subset, that means C is a complement of an open set. And by the definition of co-compact topology, C is compact in R usual. But here we are proving that if we have a closed subset, then it is compact in R comma tau. Fine. You can think of whether these are the only compact sets. So if you can find out some set which is not compact, yeah. So actually, sorry, if you can find out some set which is not closed but compact, then it will be very nice for you. Actually, I have got some set which is not open, but it's not compact. Say 0, 1. Okay. If you consider this 0 and 1 interval, then this is not compact in R, comma tau. Note that this set is not compact in R with usual topology, right? Why? By which theorem? Some of you told a little ago. So by
Henry
which
Borel
theorem?
theorem. Henry
By
Borel. Henry Borel.
what? Henry Borel?
Heine Borel.
Heine
Heine
Borel
Borel.
theorem.
Hein-Borel theorem. Yes.
Okay.
Be confident. Okay, by Hein-Borel theorem. Fine. So this set is not compact. It's an exercise. Okay. Please do it. Fine. Now let me move to problem number 2. So see, this problem is still not. I'm not saying answer is incomplete so far. Like we need to find out a compact set, but so far we determined that all the closed sets are compact, and even R itself is compact. But could not find out all the compact set yet. Fine. Okay. So let's move to the second problem. Example of a T1 space in such that convergence sequence may have more than one limit. Could you give an example?
Cofinite topology on natural numbers.
Yes, cofinite topology in natural numbers. So let x is equal to n and tau be cofinite topology. Okay. Not like that. Tell like n with cofinite topology. It is much nice to say. So why it is so? Can you give an example after taking this set? So yes, we have taken an example of a T1 space with cofinite topology. Now give me an example of a sequence which converges to more than one point. Convergence sequence, of course.
Xn equals to n.
Yes, xn equal to n. Then where does this sequence converge? Is it a convergence sequence first? Tell me whether it is a convergence sequence or not. Is it?
Yes, sir.
Why? Why?
It is eventually in every infinite set.
Eventually in. See, give the complete argument. Okay. So because if you take any element, say m belongs to n, fine. Any element, so it's a fixed element. Now you an open set containing m, right? Then what is n minus u? It's a finite set. Say m1, m2 up to mk, right? Now, so if you consider n is greater than mk, then this will implies n belongs to u. That is xn belongs to u for all n greater than mk or greater than equal to mk plus 1. This is the definition why this sequence convergent, right? Now what we have proved, we have by taking an arbitrary element, we have proved that this sequence convergent to that element. So we can say this sequence xn in particular n converges to every element, right? So if your space is not Hausdorff, then a convergence sequence may have more than one limit. Fine. Okay. So now this problem, it's a problem on metric space. taken from the book by Aliprintus and Barkinshaw. Right. So what's the fixed point? Do you know a fixed point of a function? X to x. So what is the fixed point?
fx equal to x.
Yes, x naught or x is called fixed point if fx naught equal to x naught. Now the condition given that x comma d is a compact metric space. Okay, and if from x comma x this function satisfies that if you take the image of f x and y under f, then their distance is strictly less than distance between x and y whenever x and y are not equal. So of course even they are equal, then these two are same, being 0, right? So you have to prove that this space has a unique fixed point, right? So okay, let's first prove that this set has space has a fixed point. So consider a function phi from x to say r by phi of x distance of f comma fx, right? Is it continuous?
Yes, sir.
Yes, sir.
Why?
Sir, from given condition, because d of fx comma fy is less than d of x comma y. So
Huh?
whenever dxy less than delta, then df of x comma f of y less than delta.
Huh. And using those, you can prove that this function is continuous. Okay, I'm leaving it for you to verify. Right? Now you see that image of a compact set under a continuous function is compact, right? More
Yes,
than
sir.
that, we can say that, and therefore, if you look at the image of phi, this will have a maximum element and a minimum element, right? Every compact subset of R
Yes,
has a
sir.
least element and has a greatest element. In other words, if we have a real valued function, it assumes a least element and a greatest element, right? Supreme and infimum.
Yes, sir.
Yes. So phi have some uh, least element, at least as of now. Now suppose suppose there is no fixed point. Fine. Then what happens? For all a belongs to, or for all a belongs to say x, if a not equal to what?
A.
If a not equal
A.
to a,
A.
then what you can say? Then we can say phi of fa. What it is? It is distance of fa comma f of a, right? By definition, phi of x is equal to d of x and fx. So phi of fa will be d of fa and f of ffa. But by the definition of this metric, we have d of fx comma fy is strictly less than dx comma y. So this is strictly less than d of a comma fa, right? But what is this? Is by definition phi of a. So phi of fa less than phi of a, right? So could we get a minimum element here? Means if we now, so this is now, so we can apply up to dot phi of f power n a and so on. Okay, so and this will go. So we can see that this set does not have a minimum element. Okay, which is a contradiction. And for the uniqueness, you can verify by yourself that if there is two more points, two fixed points, then fx is equal to x and fy equal to y. So from the definition, we will have d of fx comma fy will be d of x comma y, and here which is strictly less than dx comma y. This is not possible. Let's say 1 is less than strictly 1. This is not possible. So we can say there is unique fixed point. Fine. Now this one. You had an example as a question in your exam that whenever f is continuous and you had some space f is continuous, and if for a given convergent sequence, if fxn has a convergent subsequence, then these two are if and only if condition, right? Fine. And here and there you also had the graph of f is closed or not was a crucial role. But here, if we take a function between two metric spaces, and then if the range space is not compact, then here we can see the graph of f, the graph of function may be closed with respect to the metric, but f need not be continuous. Fine. So I will just give the example here and leave it to you for you to verify, because I want to show something for you, so something like tube lemma and its application on that application to the fact that when our first projection will become a closed map. So for this problem, I just leave it by giving a function whose graph will be closed, but the function is not continuous. So can you give some spaces and some such function if you have in mind? That your space x comma d metric spaces y comma rho, can you give a function f such that what graph of f is closed but f is not continuous?
सर g of equal to x comma 1 by x.
g
ये
of
वो
x
फर्स्ट
is
फर्स्ट
equal
क्वाड्रेंट
to
में ग्राफ बन जाएगा एंड थर्ड में बन जाएगा, बट कंटीन्यूअस तो नहीं होगा.
हाँ g of x is equal to x comma
1 by x
x
and x
comma
belongs
1
to
by
r.
for all x belongs to
r
हाँ
r minus 0.
हाँ उसके बाद r का 0 का क्या होगा? ये तो कंटिन्यूस बन गया ना. Whenever x is not 0, this function is continuous. If x equal to 1 by x is continuous.
बट सर वो फर्स्ट एंड थर्ड में भी तो बनेगा ना ग्राफ.
हाँ
फर्स्ट एंड थर्ड
फर्स्ट
क्वाड्रेंट में.
एंड थर्ड मतलब
इस ग्राफ इसका कैसे
सर
बनेगा?
सर अगर 0 से 1 के बीच फंक्शन x ले लें और 1 से 2 के बीच 2x ले लें
हाँ
तो सर वो क्लोज्ड हो जाएगा, बट
हम्म
कंटिन्यूटी ब्रेक हो जाएगी सर एक पॉइंट पे.
ये this is also nice. 0 to 1 x this one and 1 to 2 2x. 2x मतलब वो थोड़ा ऐसा वो हो जाएगा ना, उसका स्लोप ज्यादा हो जाएगा. मतलब whenever it is 1 it will be this kind of, right? Let me show you this kind of function, right? It is not continuous at x. Yes, this example will also work. For this example, it was saying whenever we take x goes to 0 plus, it will will move to plus infinity, right? Right? Who told this problem?
Yes, sir.
And whenever x goes to 0 minus, then this function goes to minus infinity, right? And your argument was for this reason the function will not be continuous, right?
Yes, sir.
Why? Why? Actually, we are verifying the continuity of a function, continuity of the function at a point 0, but 0 is not in the domain. Have you defined the function at 0?
No, sir. No, sir.
Then तब क्या होगा? Actually, you have to define whenever you are defining some function, you have to define for everywhere. Yeah, this is also a function you have defined here. Your domain is r minus 0, but in this case, the function is continuous, right? But if you consider this function 1 by x when x is non-zero, if you define it as 0, or even if you define it as any or 0 or any number, any real number, say a, for x is equal to 0, then this function will not be continuous, because at 0 plus it is going to infinity, 0 minus going to minus infinity. Even at the point 0, the limit does not exist, right? Yeah.
Yes, sir. Yes, sir.
Actually, we verify the continuity of a function in its domain. Fine. So if the
Right.
function is not in the domain, then we could not say about the continuity. Yeah, of course we can say about the limit. For the existence of limit, we verify it for on a closed subset of the domain or the closure. But to verify the continuity, we should verify the continuity of a function at some point in the domain. So we don't have to worry about the points which are not inside, which are outside of the domain. Fine. Okay, then it is fine. So verify all the other things, whether its graph is closed. Yes, of course, that guy given an example that this is closed. This is a closed graph, but it's not continuous. You can also look at this example also. We have this one, and the graph of this function will be one is this way, another one is this way, and including the point 0, right? Or if you take any other point, then it will be at the point 0, it will be somewhere here or somewhere there in this way. Okay. So, but in this case, it will not be closed. Sorry, in this case, the graph will be closed. The function is not continuous. Fine. Now, this one. This is easy. I think you all can solve this problem. So read the problem that if we have a continuous function between two topological spaces, and if x is compact, so x is compact, okay, and y is Hausdorff. To prove that f is a closed map. Yes, any argument for this problem? It's
Yes, sir.
very easy.
Take arbitrary closed sets A
Who is
of
saying
X.
this?
A
Piyush.
subset of X.
What about others? Piyush, तुम थोड़ा रुको. Friends को
Yes,
भी chance दो. हाँ,
so we
सार्थक.
can take any closed set,
हाँ, close set.
and since
Yes.
X is compact, the closed set will also be compact, and since
Yes,
F
is
is
subset of
continuous, it's
X.
immediately,
C is compact. Then
and C is compact and F is continuous, so F of C is compact.
so this implies it is closed. This implies f of c is compact. Then
And since Y is Hausdorff, so FC is closed.
and y is Hausdorff. So this implies Fc is every compact subset of a Hausdorff space is what?
Closed.
Closed.
Yes,
Yes.
closed. Yes. Fine, fine. Good. Please be confident. Okay, while you are saying something. That confidence matters a lot whenever you are giving some interview. Sorry. He's not here. He's in a meeting. Maybe you can wait for 10 to 15 minutes. Sorry, someone is here. Okay, so look at this problem. Let tau and tau dash be two topologies on a set. So you are given a set X, but two topologies. One is tau, one is tau dash. Fine. It is also given that both x comma tau and x comma tau dash are compact. Fine. Then what happens? Then either tau equal to tau dash or tau and tau dash are not comparable, means none of them, or tau this and okay, either they are equal or not, or they are not comparable. Fine. Do you know the definition of comparable? Comparability? Or what do you mean by comparable? Two sets or comparable means whether means none of them is a subset of other, or none of them is contained in the other. So how do you proceed for this? Any argument? It is given compact and Hausdorff. Yes, of course, Hausdorffness is important. Okay, then the topologies are either equal or they are not comparable. Okay, fine. So suppose yes. Can you take 2 minutes to think of? So how to proceed for this? Do you know this result? Suppose f from x to y be a continuous and bijective map where x is compact and y is Hausdorff. Then what can we say about this map?
Then F will be
F
homomorphism.
Then yes.
F inverse is also continuous.
Then F inverse is also continuous. And therefore F is a what?
Homeomorphism.
Homomorphism. Now suppose this condition does not hold. So suppose they are not okay. They are okay. It tells they are not comparable. Okay. So we assume suppose they are comparable. Okay. So suppose tau and tau dash are comparable. Okay. And let's say tau is contained in tau dash. Fine. We want to show that tau and tau dash are same. Can you consider the identity function? Identity from say, x
tau
comma
prime.
tau dash to
X comma tau.
yes x comma tau. Then what happens? This is a bijective map, right? Is it continuous?
Yes, sir.
ID is continuous identity. So by this result, identity is a homeomorphism, right? Right? So now if you take any neighborhood or any open set from here, sorry. Okay, now if you take any open set from here, then its inverse image will be, oh, what I proved. Yes, then okay. Once we get homeomorphism, then image of open set is open, and inverse image of open set is open, right? So take an open set here, its image will be set itself, so it is open here. And if you take an open set here, its inverse image will be open in here, so it's open. We're done. Right? Clear? Okay, so tell me one thing. Suppose you have a map, say, okay, suppose you have the identity map from R to R. Suppose you have some topology tau 1 and here tau 2. Can we always say this map is continuous? Yes. So can we always say this map is continuous?
No.
For any topology? What if we take this tau 2 as discrete and this tau 1 as usual? Then what happens? What are the open sets here?
Every set.
Every set is open here, right?
Yes, sir.
So take a singleton set, say A is open here, but what is its inverse image? This is a singleton set. Is it open in R with usual topology?
No, sir.
So that's why identity map is not continuous. So you see, even identity map is not continuous. Where we are living. Okay. So anyway, those are the problems I wanted to discuss. But now I want to tell you something new. It's called tube lemma. Could I do that or leave you for the day? What do you want? Yes, no. Actually, okay, let me just give you the statement. Okay, so tube lemma. Where was that? It's very useful to them. Okay. Let X and Y be two topological spaces where Y is compact. Okay. See here with X there is some topology tau 1 and with Y there is some topology tau 2. I am not writing this tau 1 tau 2 and I am simply writing that X and Y are topological spaces. Okay. So it is understood that there is some topology. And with respect to that topology, Y is a compact set. That's all. Fine. Y is compact. Then what's del? So suppose if N is an open set in X cross Y containing the strip or the slide or containing the set X naught cross Y. Okay, for some X naught belongs to X, then there exists a neighborhood W of X naught in X such that W cross Y subset of N. Okay, so this lemma is called the tube lemma. Why, let's understand why this lemma is called tube lemma. Suppose this is your space X and this is your space Y, and you are given that your space Y is compact. Fine. Suppose here is the point X naught, and you consider the line, and suppose you have some neighborhood, say N containing this set. So this kind of neighborhoods are there. Okay, or say you have this one and you have a neighborhood here like this. Then you can prove that there is some say W. There is some say W of which is neighborhood of X naught. This is X naught such that W cross Y means this entire set. This entire set lies inside of that N. So this is your N and this set is W cross Y. So tube lemma says this one. Fine. Clear? Could we prove this one or leave it just as a statement? Okay, so let me leave the proof for the moment. I want to tell you the application. So you know the projection map, right? X cross Y to X given by phi 1 X comma Y equal to X. So what can you say about this map? This is continuous and open, right? Could you say the map is closed?
No, sir.
Is phi 1 a closed map? Is it a closed map?
No, sir.
Who is saying this? This is not a closed map? Tell me. Who are agree that this is a closed map and who does not agree that it's not a closed map? Okay. Let me give you the some closed set also and to verify. Say here X and Y are any set. Okay, I am not giving any restriction here. Suppose you have this R cross R. Okay, and suppose you have this one, this set. So the set X comma 1 by X such that X greater than 0. Okay. Tell me whether what is its image and whether it is a closed set or whether the map is closed map. Tell me this one.
Sir, image is 0, infinity open interval.
Image 0, infinite open interval. Then
Set is not closed, so it is
it is
not
not
closed map.
closed. So how many of you agree with him that this the projection map need not be closed? The first projection need not be closed. Whenever you are giving a topological two topological spaces, that this space need not be closed. So how many of you agree with this? You can raise your hand using this kind of emojis. And how many of you agrees that it's not closed? Okay, Sita Basu, is it, what is your argument? Is it closed or not closed?
Not closed, sir.
Okay. Sanju Bala, is it closed?
Not closed, sir.
It is not closed. What about others? Ankit,
Sir, not closed. Agree.
it is not closed. Fine. Sarthak
Yes, sir.
Raj,
Not closed.
it is not closed. But in exam, many of you wrote that the projection, if we take a closed set, graph up is closed. Therefore, if we take the image, it will be closed map, and you lose marks there. Okay, that's why I have used. I thought I should stop there, but that's why I taught you this one, this tube lemma, and we will use tube lemma to assume that whenever it is compact, then this map is closed. Fine. Okay. So now for the moment, so pi1 is not closed. I also taught you in say I think in second or third tutorial sessions that this map need not be closed by giving the same argument or same example. Anyway, so suppose, okay, so pi1 need not be closed in general. Okay. Now assume that Y is compact. Assume that your space Y is compact. So can you please look at this lemma and try to verify whether it's a closed set or whether it's a closed map. Okay, I'm giving you a little argument. Or so suppose you say B a closed set in X cross Y. Okay, now look at pi1b. You have to check whether this is closed or not. Fine. So can you take 2 or 3 minutes to verify whether it's closed or not? What else to teach? So okay, so suppose we have to prove that all the closure points are inside, right? That's mean if we take a point from outside, that point should not be a closure point of that set, right? So suppose a point say x0 does not belongs to pi1b. Fine. Our aim is to find some open set V of or open neighborhood V of x0 such that V intersection pi1b is empty, and this will lead you that x0 is not in the closure, not a closure point. So therefore we will say there's a closed set, right? Now look at this one and say, yeah. If we look at x0 cross y and c, what can you say about cross y and b? Is there any intersection? So if we take a point say x0 comma y, will it be in b?
No, sir.
Why?
Because sir, x naught does not belongs to pi1b.
Yes, because if it is in b, then we just take pi1, then pi1 x0 comma y will be x0, which will be in pi1b. Therefore, this is not in b, right? So x0 comma y is not in b. In fact, this space x naught cross y is not a subset of B, right? So since for each x naught cross y is not in B and B is a closed set, so what you can say? There exists a neighborhood, say ny of x naught y, right? Such that ny intersection B is empty, right? Fine. Oh, again, I need to extend somewhere. I don't know. Anyway, maybe I can finish it over here itself. Okay, let me erase these things because those are not that much important. So this one and this one I should erase just by saying that. Just need the spaces. That's why actually you have understood. So I can erase those like blackboard. So if you look at this, also no. If we take x naught is not here, what we have proved is that x naught cross y is not a subset of pi o1 b, or this is these two are disjoint actually. Okay, so not like this, write it as, because no point of this set, it's a set actually. This intersection, this is empty. Fine. Now pi on. Oh, is it something wrong I have written?
Sir, pi 1b is singleton set.
Pi 1b singleton set. Who said this? Yes. Is there anything wrong?
Yes,
Actually,
sir.
this. Yes. What is wrong here?
Sir, we can't take x naught cross y intersection pi 1b.
Ah, exactly. Intersections can be happen between two sets which are coming from the same superset, right? So pi 1 x comma y intersection B is empty, right? So therefore what what we have? Okay. So now if you take an element x naught comma y, then this point will not be a closure point of B, and therefore there exists some ny which is a neighborhood of x naught comma y such that ny intersection B is phi. So there exists ny such that this is phi. Now take the set n as union of y ny, right? Right? This union will be a open set containing what? Containing see x naught comma y, for each y x naught y belongs to ny. X naught comma, let me write x naught comma y such that this happens. Now x naught comma y belongs to ny. Then what does this union contains? Can we say x naught cross y belongs to n? It's a subset of n.
Yes, sir.
Why it is subset?
Every point is contained in some ny.
Yes, every point contained in some ny. Because if you take x naught comma y, it contained in ny. That is the way we have chosen ny, right? And therefore this is arbitrary union of open set, and therefore it is open in x cross y, right? Now apply this result. So okay, let me tell you something more. N is an open set in x cross y containing x naught cross y. Now look at this lemma, this tube lemma. X and Y topological spaces, Y is compact and N is an open set containing X naught cross Y. What can we say about this then? There exist. So by tube lemma, there exists a neighborhood W of X naught such that W cross N subset of, sorry, W cross Y is contained in N. Fine. Tell me one thing. What is the intersection between N and B? Can we say N intersection B is empty? Yes. N intersection B is empty. Look at here. NOI intersection B was empty. Fine. And N was union of Y belongs to Y, NY. Then what about N intersection B? This is union of Y belongs to Y, NY intersection B, right? Union of Y belongs to Y, NY intersection B. This is empty for each Y, so therefore is empty. Clear? Set theory. Clear? Yeah,
Yes,
you
sir.
should tell something, right? If you do not respond, then if you're not getting, please tell me. I'll repeat because nothing to anyway. So W in cross Y is an open set contained in N. It's a neighborhood of X naught cross Y. Now you see, right? Yeah. Yeah. N intersection B is empty. What can we say now? What if we take pi 1 of W intersection Y and then intersection of pi 1 of B, what happens? This is
Empty.
yes, this is empty. Sorry, it is W cross Y. Right? Because W cross Y is subset of N and B intersection N is empty. So if you take the pi 1, then pi 1 of this intersection pi 1 of B is empty. And now this one, if you look at this set, this is actually W, right? So W intersection pi 1b is empty, right? So what we got? W a neighborhood of X naught such that W intersection pi 1b is empty. So W is not in W is not a closure point of pi 1b. So what we have taken? We have taken a point outside of pi 1b and proved that this point cannot be, this point is not a closure point, right? So what we can say that pi 1b is equal to, therefore pi 1 of b is same as pi 1 of b closure, and so pi 1 of b is closed, or pi 1 is a closed map. Pi 1 is a closed map. So what I can say is that whenever you are given the space Y is compact, then the projection map for the first projection pi 1 from X cross Y to X is a closed map. Okay, fine. So that's all for the day. So tell me if you have any doubt at the end. So if you have any doubt regarding this proof or anything, or if you have anything, so you can ask. Yes.
So please repeat last statement.
Which one?
So how it is empty? Pi 1 W cross Y intersection.
Yes, sure. I will. N intersection B is empty, right? And W cross Y subset of N. So W cross Y intersection B is empty. Fine. Fine. Now consider the projection. Is it clear? Actually, you see, actually we have this kind of neighborhood and this is containing all those. So these all black sides. Fine. This W cross Y is consisting of all these elements. You might have think that if we take 1 point from here and 1 point from here. So suppose this is your B and this is your this is from your W cross Y. Then then if we take the projection, then their image will be same. But this is not the case. Your case is your W cross Y is this one, this set. So let me write properly. Your W cross Y is actually this set containing all the points, okay, whose first coordinates lies in W. And therefore, since this is empty, your B is somewhere outside. Fine. That is why whenever you are taking projection, its projections are lying in W. But the projection of the map elements of B are lying in outside of W. That is why if we take the first projection, this will become W, but this will become pi 1B. And by this diagram or diagram kind of things which I have said, that since W cross Y intersection B is empty because Y covers, because Y is your range, right? So Y is your second coordinate of the product space. So and therefore we can say W intersection pi 1B is empty. Okay, clear? And as I said, there will be no element of this form. So suppose you can think of there are some element, you can have some horizontal line, and from this horizontal line, some of the elements, this element is in W cross Y, but this element is in B. Then if we take the projection, then they might project a same point, or in other words, if this is non-empty, okay, so let's do something else. So in a different way, suppose some X belongs to W cross pi 1B. Right? Since it is in X is in pi 1B, there should be some Y such that X comma Y not belongs to B. Right? But X not, sorry, this, yeah, X comma Y not belongs to B, but X belongs to W and Y not is Y. So where? So X comma Y not belongs to W cross Y, right? This is contradicting the hypothesis, contradicting the condition that W cross Y intersection B is empty, and therefore we will take the first projection. Then this will give you the empty set, means the intersection will be empty, and the first projection of this is W, and W is open set containing X naught, and therefore pi 1b is not a, sorry, pi 1b is a closed set. Fine. Is it clear?
Yes, sir.
Okay. Fine then. Stop recording.